This is part 8 of the series Three-Dimensional Solids. In this part, I'm going to continue with a couple of more exercises and examples of how to find the volume of three-dimensional solids. For the first one, we have this nice composite solid. This is a regular pentagonal prism with a pentagonal pyramid on top, and both of these are right solids, which means the axes are perpendicular. The lateral face here is perpendicular to the base. So to start with, in order to find the volume of these solids, let's go ahead and write the formula for the volume of these solids. Let's go ahead and start with the volume of the prism. What we have is the overall volume, we'll call this volume total, is equal to area of the base times height. That's the volume of this prism. The volume of the pyramid will be added to that, so that's 1/3 area of the base times height. As is always our standard practice when finding the area of a regular polygon, we need to work on this triangle inside here. So we need to create a triangle inside here and solve for that triangle. So I'm going to create that right here. I'm going to put in my apothem, which is right here. And these are little right triangles. Since this side length is 6, this whole thing is 6, this side has to be 3. We've learned that a long time ago, that in any kind of isosceles, and of course this is isosceles because these radii are all congruent. So that gives us this side length, and we're looking for the apothem. And the reason we're looking for that apothem is going back to this formula. Area of the base is 1/2 perimeter times apothem times the height here. So this is area of the base, and the height is here. And again, this one would be 1/3, and this area of this surface is going to be the same as this one. So it's going to be 1/2 perimeter times apothem again. So this area of the base is going to be the same in both cases because these bases are identical. And that's times that height. So we need this apothem. In order to get this apothem here, we're going to have to find this angle because we don't have the length of the radius to solve this right triangle using Pythagorean theorem. Now, in order to find this angle, we need to understand, as usual, that we have one of these triangles for every side of the polygon. That means there's 5 triangles. That means there's 5 of these central angles. So we have 360, which is the total number of degrees in a circle, divided by 5 of these central triangles, or central angles. That gives us 72 degrees. So if this angle is 72 degrees, then this one has to be half that, which is 36 degrees. Now we have enough to find this. I'll go ahead and put an apothem here, an A for apothem. And so we're going to use our trig functions. Some old horse, nope, can't use it. Caught a horse, can't use it. Taking oats away. So it's tangent. Tan 36 equals oats away 3 over apothem. Solving for apothem, multiply both sides by A. So these cancel out. A tan 36 equals 3, divide by tan 36. So apothem equals 3 divided by tangent of 36. And when I get this calculation, I'm going to store it in location A. I always like to circle them. And so that gives us our apothem. And now we're just about ready to start plugging in for our formula. Now this value is about 4.13. I'm not going to use this approximated value. I'm going to use the stored value in my calculator. Let's go up here and start solving for this. So big B is going to be 1/2. Now the perimeter. Perimeter is 6, the side length, times the number of sides. So 6 times 5. Times the apothem that I stored. So we'll make sure we know that that's a stored value. Times the height. Well, the height of the prism is 8. So that's times 8. Plus 1/3. This is just area of the base, so I'm going to put that in there because I'm going to actually store the area of the base once I get it. And that's times the height of this pyramid, which is 7. Let's go ahead and calculate our big B. So big B is 1/2 perimeter, which is 6 times 5, or 30, times the apothem that I stored. And that gives me approximately 61 point, well, we'll just call it 9. Now we can go ahead and just substitute those in. Let's put some equal signs in here to indicate that that's still our volume. So we have big B from our calculator times 8 plus 1/3 big B times 7. And that is what you put in your calculator, and the final result is approximately 640.0, we'll call it 0.2. It's 0.0175, so 0.02. So there you have it, the volume of a composite solid. If you take it methodically like this, it's not too big of a deal. So let's go ahead and work on one final problem for volume of composite solids. In this problem, we have a little bit of a different situation. What we have is a regular hexagonal prism with a square pyramid cut out of it. You can see that this is not going to be added to the volume of this prism. We're going to actually subtract out the volume of this pyramid from the volume of the prism. To start, as I've done in the past, I'm going to write down my formulas. First, the formula for my volume total. So this volume is going to be the volume of the prism, which is area of the base times height, minus the volume of the pyramid. 1/3 area of the base times height. Now in this case we have a slightly different situation. In the last problem we did, the area of the bases were identical. In this case they're not identical. So I'm going to distinguish base 1 and base 2. So this would be base 1 over here. So this is B1 and this is going to be B2. So let's start with area base 1, which is going to be 1/2 perimeter times apothem. And again, we have an issue. We don't know what the apothem is. This apothem right here. So I'm going to create another triangle here. And we're going to solve that apothem. So that's the apothem. We know this side length is 12. This side length must be 6. Now, the nice thing about this problem, it gave us a radius, which means we have this side length. So we don't really need to find our central angle this time. We can just use Pythagorean theorem. But if you notice, this is a 6, this is a 10. What we have here is actually a 3, 4, 5 Pythagorean triple with a multiple of 2. So this is 3 times 2, 5 times 2. That means this must be 4 times 2. So this apothem has to be 8. If you didn't remember that, that's fine. You can just do a squared plus 6 squared equals 10 squared. A squared equals 10 squared minus 6 squared. Take the square root of both sides. So a equals the square root of 10 squared minus 6 squared. And if you did that, you would come out with 8. Okay, well that gives us our apothem. Now we can actually calculate our big B here. This becomes 1/2. Perimeter is 12 times 6, which is 72, times our apothem. Obviously I didn't have to store that because it's a whole number here. And that comes out to exactly 288. Now we can turn to our big B2 here, and big B2 is really easy because it's just 4 times 4. This is a square base. So big B2 is 16. Now we're ready to go ahead and plug in all our values. So your volume total then becomes area of the base, which is 288, actually area of the base 1 is 288, times the height of the prism, which is 18, minus 1/3 area of base 2, which is 16, times, again, the height of the prism is the same as the height of the pyramid, so that's times 18. And that should come out to 5088 cubic units, whatever those units happen to be. All right, well that wraps up finding the volumes of three-dimensional solids relating to prisms, pyramids, cylinders, and cones. Now we're going to look at the effects of changing dimensions on volume. In this problem we have a cone, and we're trying to determine the effects on volume by doubling all linear dimensions. Just as we did with surface area, we don't really need to worry about the actual dimensions of the object to determine the effects of changing those dimensions on the volume of the object. That's all we really need to do is look at the formula. So let's bring up the formula. Here we have the volume of the cone, 1/3 area of the base times height. Break this area of the base down. The base is a circle, so it's 1/3 pi r squared times height. Now, if we want to determine the effects of doubling the linear dimensions, we're going to double the radius and double the height. So here we say the radius is multiplied by 2, I put this in parentheses, and the height is multiplied by 2. Now, the only change to the overall formula is this 2 and this 2. Inside here, this 2 is going to be squared, so this is going to be 4 times 2. We pull that 4 times 2, which is 8, out, and we have 8 times the original formula. 8 times 1/3 pi r squared h. So the effect on volume of doubling all the linear dimensions, in this particular case, with a cone, is to multiply the original volume by 8. So the new volume is going to be 8 times the original volume. And you can do that with any of the formulas for the three-dimensional solids. Just calculate, just put down the formula and calculate what that change would be, factor out that change, and that gives you the overall effect on the dimensions. Well, I hope that helped a little bit. And so in the next video, we're going to look at surface area and volume of spheres. So I will talk to you in the next video.